Alright, so today we're going to be talking about the photoelectric effect. Alright, now the photoelectric effect is when you shine light upon a metal surface and electrons are ejected from that surface. Alright, and this was one of the first experiments that was showing that classical mechanics wasn't a satisfactory theory to explain the interaction between light and matter. And eventually in 1905, Albert Einstein figured out the correct explanation as to what is actually going on here. And then in 1921, he received the Nobel Prize for this work. And actually, this is the only Nobel Prize Albert Einstein actually got, was for the photoelectric effect and not for his general and special theories of relativity like most people actually suspected. And the reason for this was that during Einstein's lifetime, the experiments were nowhere near sensitive enough to actually prove that special and general theories of relativity were actually correct. So, the photoelectric effect is the only one that he won the Nobel Prize for. All right, so how this works is we're just going to draw a little diagram here. Okay, so here I have a metal surface, and this metal has what's known as a work function. And this work function is the minimum energy needed for an electron to escape. So you can almost think of it like the escape velocity on the Earth. For a spacecraft to, escape Earth's gravity and go into interstellar space, it needs at least 11 kilometers per second to actually escape the Earth's gravitational field. Same thing here, you're going to need a minimum amount of energy to actually escape the metal. And this depends on your metal. Certain metals are going to be less, certain metals are going to be more. It all depends on which one you're actually talking about. So what's going to happen here is that if I have, let's say, a low energy photon, so this would be something like a red photon. This little red photon would come in, and it would just be either absorbed or reflected, and nothing would happen. Okay, so low energy, and by this low energy I mean here the energy of my photon is less than that of my work function. And in this case, no electron emitted. In other words, if you're below the escape velocity of the Earth, like if I just take this pen, throw it up, then it's not going to escape the Earth. So it's the same thing here. You need a certain amount of energy to actually kick that electron off of the surface of the metal. And for low energy photons, if it's below that energy, the electron might hop a little bit, but it's not going to escape. Now, if you do have one here with a higher energy photon, so this will be a blue photon, and in this case, this will knock an electron off. So here, this is going to be a high energy one, and now the energy of my photon is going to be greater than that of my work function. And then we're going to get an electron which comes off. And what we're going to be doing here is calculating, well, what is the energy of this electron? And when I'm saying the energy of the electron, I mean the kinetic energy of the electron, and also the speed velocity of the electron. Okay, so that's what we're going to be calculating here. All right, now how we actually calculate the energy of this electron is simply by using our energy conservation rules. So here, the energy of my electron is going to be equal to the energy of my photon minus my work function. Because this, of course, is simple energy conservation. The energy of the photon comes in, and it basically needs a certain amount of energy to liberate that electron, which is going to be my work function. And then what's left over is going to be the kinetic energy of my electron here. So you can kind of think about the work function as being your potential energy. So essentially, once the electron is in the metal, it's basically in a gigantic hole. It can't get out, right? And to just escape the hole, you need this work function here to actually get enough energy to actually get you to the surface, and then whatever energy is left over is going to go in being the kinetic energy of my electron. Okay, so that's essentially what this equation is saying right here. So essentially that's all the information we need to go through a little example problem for this. Oh, and then of course the other thing is just to remind ourselves, again, this is an equation we saw earlier, but here the energy of my photon is going to be hc over lambda, of course, and the energy of my electron is going to be the kinetic energy 1/2 mv squared. Okay, so essentially these are the equations we're going to be using while we plug and chug into there. So for our little diagram, we're going to say here that this wavelength here that we're going to use is going to be equal to 400 nanometers as our example. And for my metal down here, I'll say that my work function is equal to 2.3 electron volts. All right, and electron volts is a unit of energy, and commonly if you look up work functions, this is the value that the work function will actually be in. And also our conversion factor here, 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So of course joule is our unit of energy. at this point, we can just calculate stuff out from here. So first up, the energy of my photon. So right here, the energy of my photon, that's hc over lambda. Here's Planck's constant, speed of light, and the lambda that we earlier just said was right up here, 400 nanometers for our light. And of course, we just have to always convert these into meters so our units cancel out properly. And we're left here with 4.97 times 10 to the minus 19th joules. So that's the energy of my photon. Now here for my work function. So we just took our work function, the 2.3 electron volts, and we multiplied this by 1.6 times 10 to the minus 19 joules, so that gives us 3.68 times 10 to the minus 19 joules. All right, and notice these are actually on the same order of magnitude, which is usually going to happen. Oh, and by the way, the work function for this metal, this 2.3 electron volts, this is for potassium. So actually that's a real metal, not just some number I just made up there. Using this equation, the energy of the photon minus my work function, so I have these two numbers, I just have to subtract them to find the energy of my electron. So this is the energy of my electron, 1.29 times 10 to the minus 19 joules. And now what we can do is plug this into our equation to figure out the kinetic energy. Well, this is the kinetic energy, to figure out what my velocity of the electron is. And the only thing that we need to know here, of course, is the mass of the electron. So the mass of my electron is 9.1 times 10 to the minus 31 kilograms. Okay, so this is the mass of the electron. Again, this has to be in terms of kilograms because when you're dealing with the kinetic energy, you need to have kilograms and meters per second. Otherwise, your units aren't going to work out. So that means that here, so all I have to do is multiply by 2, divide by my 9.1 times 10 to the minus 31, take the square root of that, and we get here, I'll just write this out. All right, so we get here our velocity of our electron is 5.32 times 10 to the 5th meters per second. Also, this is much less than the speed of light, 3 times 10 to the 8th meters per second, which is always a good check because we can't have anything going faster than the speed of light. If we were dealing with very, very, very high energy photons where you could conceivably get velocities greater than the speed of light, then you would need a relativistic treatment. But for the stuff that we're doing here, we don't do that. All your velocities should be much less than the speed of light for this, which it is, so this is good. And by the way, if you see these units here, joules per kilogram, taking the square root, how do we get meters per second from that? Again, you just have to remember here that a joule is a kilogram meter squared per second squared, and then it's quite obvious. So if we just look here at the units, so you can see right here that my kilograms cancel out. That looks a little bit weird units, but joules per kilogram, take the square root, that gives us meters per second. All right, now what would happen here if I put in a low energy photon? Now, classically, what they expected to happen is if you put enough low-energy photons, eventually enough energy will build up in the metal that it will be able to eject an electron. So kind of like, if you're saving up money, right? If you just get, your $1 an hour, you don't have enough money to buy a cheeseburger, but, after you accumulate enough dollars after working for a couple hours, then you have enough money to buy a cheeseburger. Basically, what's going on here is that the photons, they can't build up the energy in here to start ejecting electrons. Instead, what has to happen here is that you need high energy photons basically coming in to knock an electron out directly. You can't, just build up the energy like you classically would think. Now, if we did have a low energy photon, let's just say here 400 nanometers, how would that actually work out? All right, so again, if we're dealing with a low energy photon, sorry about that, I screwed that up. That shouldn't be 400, that should be 700 nanometers. All right, if you go and calculate this out, we get, all right, so in this case, we have a 700 nanometer photon. This has a photon energy of 2.84 times 10 to the minus 19 joules. So in this case, as you can see here, the energy of my photon is going to be less than that of my work function. So if I try to figure out the energy of my electron, and we just use the same basic equation that we had over here and just plug and chug with that, what we're going to get is, and we saw here before, that my work function is 3.68. And the important point is right here, we have a negative sign. Well, having negative energy is not that big a deal, but the problem right here is that, if we would try to figure out the energy of my electron is equal to 1/2 mv squared, and remember from what we talked about before that our kinetic energy is always going to be greater than or equal to 0. So here's our big problem. Our velocity would turn out to be like an imaginary number, right? Taking square root of a negative, that's bad. So an imaginary velocity simply just wouldn't make any sense. So basically that, wouldn't work, and you wouldn't see any electrons being ejected from the metal at those wavelengths. As for, the plots of what these things actually look like, since we're dealing here with the work functions and the energy of the photons, well, normally we deal with this in terms of the wavelength. Remember that the energy of the photon is also equal to h times nu as well. So in fact, this is one way you can actually plot this stuff out, is by looking over here and saying that basically the energy of my electron is going to be equal to the energy of my photon, which is h nu minus the work function. And essentially what you can do is, if you look at this, this is simply just going to be a graph here. So this would be my frequency of my light, and this would be the energy of your electrons coming off. And what you would get in this case would be something along these lines. Basically a nice straight line like this. And this was also one of the earliest ways that they actually calculated Planck's constant. You can just look right up here. You know, there's my x, is my frequency, right? And then my slope is simply just going to be Planck's constant here. And my intercept, if you look down, that would, it would just continue on and be, intercepting, somewhere down here. But you wouldn't actually see any electrons going here. So there's going to be this minimum frequency right here where the electrons will start off. And this is going to be your cutoff frequency. And then once you have that, after there, your electrons are going to come off with increasing energy from there. All right, now in reality, when you're doing this kind of experiment here, you wouldn't just be measuring the kinetic energy of the electrons coming off. That's actually very difficult. So in reality, what you do is you'd have your piece of metal, and then you'd have reverse voltage being applied. And all you do is actually just tune that voltage until the electrons actually stopped coming off. So essentially what you'd be doing is, basically adding a little bit extra to the work function to prevent those electrons from actually coming off the piece of metal. And here's a little diagram of the experiment. A photon hits the anode and ejects an electron, which is captured by the cathode. The anode and cathode are both in vacuum to prevent scattering and absorption by the air molecules. Those electrons would then travel down the wires and be read by the ammeter, which is the circle with the A in it, and you could detect the currents. You'll also notice a voltage divider. That's the circled part below the stopping voltage adjust. Here, you'll change the voltage from the battery on the right until the current drops to zero, meaning you're applying just enough of a voltage, which is a potential, to keep the electrons from making it to the cathode. And then this is read by using the voltmeter, which is the circle with the V in it, and why it's called the stopping voltage. And this is how the kinetic energy is measured, by seeing how much potential energy it takes to stop them. It's almost like determining the energy of a bouncing ball by slowly raising a wall. When no more balls get over, you know you've reached the maximum kinetic energy of the balls. All right, and one other little thing I just want to point out is about microwaves. Now, as you all should hopefully know, you're not supposed to stick pieces of metal in the microwave because they will start sparking. Is this the photoelectric effect? No, it is not. Because right here, we were basically saying, low energy photons, can't eject electrons from the metal. But, microwaves are lower energy than visible light, so how are microwaves, causing those sparks and everything to fly off in your microwave? Well, it's not the photoelectric effect. Basically, this is more of a classical effect here. So when you're dealing with the microwave, first of all, we just have to realize the different orders of magnitude in terms of the photon wavelength and photon frequencies we're actually dealing with. All right, so visible light is around 10 to the 15th hertz. Microwaves are around 10 to the 9th hertz. And their wavelengths of visible light is around 10 to the minus 7 meters. Microwaves are on the order of 10 to the minus 1 meters. Basically, there's a million times difference between visible light and microwaves in terms of their frequency and their wavelengths. That's why, what's actually going on here is actually more of a different phenomena, and why light doesn't do this. So you can shine your flashlight on your fork, and you will not see sparks shooting off. But if you put it in the microwave, you're going to see sparks actually come off of there. And that's because when we have these lower frequencies, the electrons couple better to the electromagnetic radiation than they do when we have these very, very high frequencies. The reasons for that are way beyond this class, so we're not going to get into it. But essentially what's going on here is at these lower frequencies, the electrons are kind of like sloshing back and forth inside the metal. So if we have here a piece of metal, and the electrons inside, and now we're going to be applying here basically our little microwave coming across here. Well, the electrons are going to be affected by this microwave moving back and forth, and you're going to wind up here with, more negative charges on this side and less negative charges over on this side. So you're going to basically be polarizing your piece of metal, and it's going to act, kind of like a little antenna, as your electron charges are sloshing back and forth. Now, if you put in a piece of metal, of course, you're going to have, more negative charge on one side. Okay. But now let's say you have here something that is pointy in your piece of metal, like on a fork, right? You have a little pointy piece of metal. Well, those electrons in there are going to, come out to this side, and you're going to basically have a large concentration of negative charges in a very small space, and this is going to cause a very large electric field coming off, a very concentrated large electric field. All right. Now, when you have this very large concentrated electric field here, this is actually going to start ionizing the air molecules around there. You have basically, the electrons are literally just going to be torn off from the air molecules. When that happens, you're going to start liberating electrons, not from the metal so much, but from the air molecules around them. So now what's going to happen, you have these ionized electrons which are shooting off. Now these electrons are going to be affected by the microwave, and they're going to start accelerating. So now these electrons are going to start shooting off, in all directions over here. And of course, what's going to happen, these electrons are going to bang into some other air molecules, ionize them, release more electrons, bang into other air molecules, release more electrons, and you have a whole cascade effect. And you have little lightning bolts, which are actually formed. All right, so that's essentially what's going on. It's not that the electrons are being ejected from the metal, it's that the metal is being polarized and you get a large electric field, which causes ionization of the air, and that liberates the electrons, which cascade after being accelerated by the magnetic field and ionize a whole bunch of other air molecules, creating little miniature lightning bolts. Now, of course, notice one thing I said here, that you have to have something pointy. All right, if you've looked inside your microwave, you probably realize the inside is made of metal and you don't have little sparks flying around. Well, that's because also, the inside of the case is grounded, so if there are any little currents and stuff that's set up, those currents are safely set off to ground. Also, all the insides of your microwave are, not pointy. They should be, relatively smooth, edges. You're not going to have, if you put a spoon, and don't put a spoon in the microwave, but if you do put one in there, it's not going to have as deleterious effect as if you put something pointy like aluminum foil or a fork in there. So the basic thing here is that you need sharp corners. If you have rounded corners, then the electric field simply just doesn't get that strong, and you don't have electrons shoot off. But of course, they generally just tell you don't put metal in, because otherwise, the metal should not have a radius of curvature greater than this, and it'll totally confuse everybody. But basically, right here, you just want to make sure that you don't have anything pointy in there. Otherwise, you will start having sparks in those cases. So basically, the reason that the microwaves do that is not that they're releasing the electrons from the metal, it's that the metal is ionizing the air around it, and then that's being accelerated offward. So this is not the photoelectric effect that is actually happening here. Okay, so I will stop this here.